So now we're trying to think of pairs of numbers that add together to give us 1. After we already thought of a bunch of pairs of numbers that had a difference of 8. Now we're thinking of numbers that have a sum of 1. So you type your first number in. Let's see what people said. All right, so we have a big variety in what people submitted for this one, which is great. I love it. And then on the next screen, it's going to tell me, oh, hey, I know what your other number was. Right? Same as in the first example. As soon as we told the computer what our larger of the two numbers was and our difference, it knew what the smaller of our numbers was and the difference. In this example, it also happened for the sum. Right? My first number was -3, and the computer knew that my other number was 4. How do you think it knows? Just as in our first example, there's only one example of a number, as Joe is saying. There's only one number that when added to a given value of x will give us 1 as the sum. Right? So there's an equation that binds the two of them together. As Cashel has wrote here, that equation will look like your first number plus the second number must equal 1. Right? That's what it meant, after all, to dream up two numbers whose sum was equal to 1. So yes, it feels like it's reading your mind, but really it's just doing a simple algebra computation. Right? Okay, so same story. Here's everybody's points, all graphed on a nice coordinate system. So what do you notice about this collection of points? Right, so what we're seeing is a similar phenomenon to what happened the first time, that all of our points lie along a line. But the difference is that now, as many of you have noticed, that line has a negative slope. Let's go back to look at the graph one more time. How do we know that this line has a negative slope? What are we looking at here that tells us that? What does it mean to have a negative slope? How do you identify just by looking? Because that's what a few of you did.
Doesn't the sum have to equal? This doesn't have to be negative.
Yeah, well, you're both right. But going to what Paul said, right, it's a negative slope. Looking at the graph, not even worrying about the arithmetic behind it, we can just see that it's a negative slope because it's decreasing from left to right. Right? As we move from left to right on this graph, the points on the graph are moving downward. So that is the prototype of a line that has a negative slope. It shows you a nice summary of the pairs of numbers that you chose in both of these examples. So what I chose first was I chose 7 and -1 to give me a pair of numbers with the difference of 8. And I had -3 and 4 as a pair of numbers whose sum was equal to 1. My two pairs of numbers were different. But the question is it possible that the pair of numbers that I chose could have been the same for both cases? That's the big question of the day. Let's find out how we might be able to know. So going back to our first example, here are all of the points that you all selected that have coordinates whose difference was equal to 8. Write an equation for a line that passes through everybody's points. Secretly, we already did this, so I'm testing your memory here. So your memory has served you well, as you noticed, that we can look at this either as the equation x minus y is equal to 8. That directly gets to the original construction of how you chose your x's and y's. We wanted their difference to be equal to 8. Or, if we're thinking in slope-intercept format, we can think about it as the version that's rearranged up here, y equals x minus 8. So for here, now we can tell directly from this equation that the slope of this line is 1 and that the y-intercept of this line is -8, which squares with the picture that was in our graph. Okay. And then now here is the line from our second example. This is the line consisting of points, all of whose coordinates have a sum of 1. So if you draw the line through these points, what's going to be an equation that these points satisfy? So now your line that goes through everybody's points is going to have a similar but not the same kind of equation as the one we did last time. So Joe here has written it as x plus y is equal to 1. Jackie has rearranged that equation to get y equals minus x plus 1. I would say that you're both correct. So Jackie, tell me how you came up with this answer. Okay, so you took a look at the line and you said, well, this time it has a negative slope, and so your prediction was that the slope was -1. Yeah, okay. So you predicted that the slope was -1 and that this one here represents the sum of the two numbers. Whoops. Sum of x and y. Right, and that squares exactly with how Joe has looked at this, which he went back to the original construction and said x plus y means the sum of x and y, and that sum is equal to 1. Right, that was in fact how we got the x's and y's in the first place, and you'll see that if we rearrange that equation to solve it for y, to get the y by itself, only one step is necessary, and that's subtracting x from both sides, and in doing so, we get from Joe's equation exactly to Jackie's. Okay, so both of those are good answers to this. So what we set up for ourselves is now two equations, and we want to know whether it's possible for them both to be satisfied at the same time. The first equation is that x plus y has to equal 8. The second equation is that x plus y has to equal 1. Is there a common solution? An x and a y that not only satisfy the first equation, but they also satisfy the second equation. So that's the big thing. And if that answer is yes, then we'd also like to know how to find that common solution with algebra. So now we know that each of those two equations represents one of the lines on this graph. The line with the negative slope was our line x minus y equals 8. And the line with the, no, that's right? No, it was the other way, sorry. The line with the positive slope was our line x plus y equals 8. The line with the negative slope was our line x minus y equals 1. X plus y equals 1. Ah, man, I'm making a hash out of this. X minus y equals 8. And x plus y is equal to 1. So the question is, if you click on the intersection point of these two lines, is it true that the x and the y that are the coordinates of that point satisfy that both their difference is 8 and that their sum is 1? Don't feel like you have to type it there. Let me just get the voice vote on this one. Is it true that they'll satisfy both of these conditions? Yeah, right. If it belongs to the upward sloping line, then that means that this difference must be equal to 8. If it belongs to the downward sloping line, it means the sum has to be 1. So if it belongs to both lines, it means both of those things must be true for that x and for that y. Absolutely. Great. So we're going to go through it again with just a quick run through. Do you think it's possible for two numbers to have a difference of 6 and also a sum of 6? So now on screen number 14 here, what would you write here for the equations that you could graph that would satisfy each of these two constraints? So what did you all get for equations of to represent each of those constraints? Let's take a look here. So kind of have people's lines going all over the place here. The word is 6 implies an equal to 6 in your equation. So both of your equations are probably going to be equal 6 based on the way that they're written in English. Now the only question is, how do we represent the sum of the numbers x and y for the first equation on the left-hand side, and the difference of the two equations, or of the two coordinates on the left-hand side of the second equation? All right, so as you're hunting around to fit equations to each of these two constraints, the first of the constraints was that the sum of our two numbers needs to equal 6. So I would write that as x plus y equals 6. The second of our constraints should be that the difference, which I would write as x minus y, needs to be equal to 6. So if I were writing equations for these two things, these would be the two equations that I would write. Now, we might disagree and still both have an accurate answer if instead we wrote y minus x down here. Notice that gives me a different line, but it still conveys this idea of difference, because we haven't specified which of the two numbers x or y needs to be the larger of the two. So either way that you go on that one is acceptable. So I'm not going to police you on that one. But at the end of the day, right, so now we have it so that everybody agrees on this downward sloping line. On the upward sloping line, there's a little bit of disagreement, but certainly nothing that we can't handle. Okay, cool. So now we have equations a system of two equations that satisfy both of these two constraints. Is it possible to satisfy both of these constraints? How do we know based on this picture?
They cross it.
Yeah, exactly. These two lines have a common point of intersection. And in fact, Spencer found what that point of intersection was right off the bat before we even asked him to. What were the x and the y that you found?
0 and 6.
Right. So here, x equals 6 and y equals 0. Yep, the two lines cross at a point, and therefore both of these equations can be satisfied at the same time. Cool. So now it just walks you through a couple more examples. And what I'd like to do, let's write these equations together. X minus y equals 5. And what I'd actually like to do now that we have the graphical picture of what we're doing when we're solving a system of two linear equations, now I want to turn and look at the algebra. So how do we actually do this analysis so that we know we're getting exactly the coordinates of the point of intersection? So for this pair, we're looking for a pair of numbers that add together to give me 12, and their difference is equal to 5. So those pairs whose sum is 12 lies on this red line. Those pairs whose difference is 5 lie along that line, and there is a point of intersection, so we know that both of these equations may be satisfied by the same x and the same y. So if you have these equations in your grapher, make a prediction. What do you think the coordinates of this point of intersection are? X value for this intersection is between 8 and 9. The y value is in between, somewhere between 3 and 4, right? So let's just split the difference in half. If we don't know anything more specific, let's just split the difference in half so that this is 8.5. Turns out that if you click on a point in this grapher, it will actually show you the coordinates of that point. So 8.5, 3.5. Great. So that's, graphically speaking, that's what we expect the coordinates of this point to be. Now let's get our hands dirty with the algebra. What we want to do next is develop the sum of the toolkit to take two linear equations and to find their common solution without having to rely on a graph or a technology tool.